Hi friends, I'm going to solve two angular momentum questions here. One is about a rotating figure skater. He opens his arms and then takes his arms in. And some values are given, some values are asked. Main idea here is initial angular momentum is equal to final angular momentum. So let's read the question. A figure skater with his arms and legs expanded spins with an initial rotational speed of 2 radian per second. So rotational speed, we use omega to represent. Omega initial here is 2 rad per second and has a rotational inertia of 0.8 kilogram meter squared. So initial rotational inertia or moment of inertia is 0.8 kilogram meter squared. As he draws his arms and legs in towards his body, his rotational velocity becomes 4 rad per second. So he's changed now. He draws his arms in, and rotational speed or angular speed changes to 4 rad per second. That's the unit for angular speed. What is the final rotational inertia? Determine his final rotational inertia or moment of inertia. That's a very simple question and you must not miss. General idea again is L initial is equal to L final. Let me rewrite that. And angular momentum is also a vector, don't forget that. To find the direction of the vector, let me show you instead of drawing it. Not drawing here. We roll our fingers along the direction of rotation. That would be the direction of well, omega generally shown, but direction of L and omega is actually in the direction of our thumb. But when you look at the picture, roll your fingers along the direction of rotation. Let me put here actually rotation. And your thumb will be showing the direction of angular momentum L. So over here, the both rotation direction is the same, so we don't need to worry about the directions. They will be the same direction. We'll put in the magnitude. So I initial, omega initial equals I final omega final. That's the idea here. We know everything else but the I final. We'll find that, leave it alone, divide each side by omega final. We'll have I final is equal to I initial omega initial divided by omega final, and values are I initial is 0.8 kilogram meter squared. 2 rad per second is initial angular velocity, and the final angular velocity will be 4 rad per second, and the answer will be 0.4 kilogram meter squared. Here you can nicely see these guys cancels and the unit left is kilogram meter squared. This question is more involved in here. I put in this picture how we calculate the moment of inertia for or rotation inertia for several general shapes, geometrical shapes we have. What is happening here is that Joey is in the center of a merry-go-round, and merry-go-round is rotating with an initial angular momentum. Then Joey walks away to the edge of the merry-go-round, and what is the final angular momentum? What happens here is, again, moment of inertia for Joey changes. We have two different objects here. We have merry-go-round and Joey. I'm gonna give them names 1 and 2. So let's call Joey 1. We have I1 initial, omega 1 initial would be equal to omega initial because it's rotating together with the merry-go-round. But they would have different angular rotational inertia. I'm going to call the merry-go-round I2 initial, and omega initial is also equal to omega 2 initial. So we have an L initial total, and we'll have an L final as well. An idea will be L initial is equal to L final. In this case, we're going to write L1 initial plus L2 initial is equal to L1 final plus L2 final. Moment of inertia for merry-go-round we will calculate using the moment of inertia of a disk, solid, cylinder, or a disk. That's the shape the merry-go-round would be. So I2 initial, I2 final will be the same. Not changing anything in here. But I1 initial will be 0. If a mass in the center of rotation, moment of inertia or rotation inertia is 0. I1 final, however, will have a value non-zero. And if we have an object like a mass or person staying at the edge of a rotating disk or rotating circle, the moment of inertia is simply defined as m times r squared. That's it. So I1 final will be this. I2 initial, I2 final will be same. Well, this is I2 initial here, because nothing is changing about the merry-go-round concerning its moment of inertia. And we'll use those to calculate our initial and final angular momentums. So let's put this in here. I1 initial omega 1 initial plus I2 initial omega 2 initial is equal to I1 final omega 1 final plus I2 final omega 2 final. This is 0 because I1 initial is 0. Why is it 0? Because it's center. If I look at this equation, R will be 0. So whenever there is a rotating object that is in the center of rotation, there is no moment of inertia. Omega 2 initial is omega I, and their final angular velocities will be same, so omega final for both. So here's what will be left. Let's go ahead and call these I2 because they are also the same. So column 1 name I2 omega initial, then we have here is equal to I1 final omega final plus I2 omega final. We can rearrange this, take the omega final parentheses and write it I2 omega initial is equal to I1 plus I2 omega final. And then we'll solve for omega final from here. I2 omega initial divided by I1 plus I2. Again, they have the same final angular velocity because the person is rotating with the same angular velocity at the edge of the merry-go-round. That's the idea here. And the given value is Joey's mass is 36 kilogram. So I'm going to take Joey's mass as actually M1 here. Let's put them over here. They put them, but I'll call them new names. M1 is 36 kilogram. I'm going to need this for calculating I1 final. Merry-go-round will be M2, 200 kilogram. It's rotating at an angular velocity of 2.5 rad per second. So 2.5 rad per second is the initial angular velocity. While it is rotating, Joey walks out to the edge of the merry-go-round 2 meters from its center. So this R is equal to 2 meters. What is the angular velocity of the merry-go-round and when Joey gets to the edge? So omega final. We already walked through the question. So it's the changes. Joey walks to the edge. Omega final will change because total moment of inertia of him will change, and that will change the omega final. So all we have to do is we walk through how to find for omega final already. We will calculate I1 and I2 simply. This would be I1 final actually. So let's find I1 final first. That's easier one. It's just mr squared, mass of Joey, times the distance squared. So I1 final is equal to m1 r squared, 36 kilogram times 2 meters squared. Once you put these in, you will find Joey's final angular rotational inertia, to be 144 kilogram meter squared. And I2, initial and final, are the same, not changing. We'll use this equation. It's given in here for a rotating disk. 1/2. Our mass will be m2. R is the same, r squared. So 1/2, 200 kilogram times 2 meter squared. I should put this one in the same format here. You guys will be confused. We're taking square of all, not only the meters. So we'll have 4 here. Okay, and that will give us a 400 kilogram meter squared as 400 kilogram meter squared as the final and initial angular rotational inertia of the merry-go-round. Now all we have to do is insert in the values. We know everything now, and solve for omega final. Let me change the color here. We'll say omega final is equal to, we already found that it should be I2 omega initial over I1 plus I2. And 400 kilogram meter squared times omega initial was 2.5 rad per second. Divided by I1 plus I2, we found I1 final plus I2, we found I1 final to be 144 kilogram meter squared plus 400 kilogram meter squared. And the result of this will give us a 1.84. Alright, my computer is stuck here. Okay, I'm going to erase this and put the value here. So omega final from here will be 1.84 rad per second. He increased the moment of inertia. As the moment of inertia increases, angular velocity would decrease. We found a smaller angular velocity, so that will make sense.